So this video will look at several examples of limits, limits of both exponential functions that have a decay or a growth factor, and also some continuous exponential growth functions that could either continuously grow or continuously decay. And again, those are extremely similar to the regular exponential growth. It's just the continuous grows a little faster. But the limit idea is still the same in that limits are essentially function values, what the y value does as the x value behaves like you're told in the problem. So we'll start with a few exponential functions. This first example is going to look as the limit as x goes to infinity of the quantity 5 plus 3 times 0.9 to the x power. So to begin with, the 3 times 0.9 to the x power, that is a decay function. It's the number 5 plus a decay function, so it's really the graph of a decay function that's going to be bumped up 5 units on the y-axis, and we'll discuss that more when we do transformations. But for now, if you take a decay function and make the x value get infinitely large, then what happens in decay functions, regardless of what the initial value is, it decays and it essentially tries to decay to nothing. That's what decay means, decay away to nothing. So if you take that portion of this function as x goes to infinity, that 3 times 0.9 to the x power goes to 0, and all you're left with is 5. If you graph this function, which I tried to switch back and forth calculator to show you, but it kept interrupting the recording, so I will graph it for you on picture-wise. So if we graph this function, it actually looks like this, except it doesn't exactly approach a horizontal asymptote at 0. It actually tries to approach a horizontal asymptote at y equals 5, and you can actually go to the table on your calculator and make the x values get large, like 100, 200, 300, and you'll start to see that that y value is like 5.00000, and it keeps going, and then it just gets closer and closer to 5. It doesn't actually ever become 5, but it just gets closer and closer to 5. So you can see as the x values get infinitely large, what the function values do, or the y values, as the y value goes to the value of 5. So that's why we say the limit of this function as x approaches infinity is 5. All right. For the second example listed here, we're looking for the limit as x approaches infinity of 8 minus 2 to the x power. So 2 to the x power is an exponential function. The variable input is the exponent. 2 is a growth factor. It indicates doubling, growing at 100% from what you started with. But the fact that it's subtracted sort of makes it do like a reflection over the x-axis. And if you graph this function, it actually does this number. So you can see as the x values here get larger and larger and larger, the function shoots off to negative infinity. The other way that you can think about this is if you had the quantity 8 minus 2 to the x power, and those x values got infinitely large, you would have the number 2 raised to an infinitely large power, and that number is just going to keep getting bigger and bigger, like 2 to the 5th, 2 to the 8th, 2 to the 100th, 2 to the 275th, whatever. It's 8 minus an infinitely large number, and regardless of how infinitely large that is, you're going to subtract it from 8, and your answer will be a negative infinitely large number as well. So here, for the limit of this function, as x gets infinitely large, as x goes to infinity, the function behavior and the function values will actually go to negative infinity, and that is the answer to the limit value for this function, negative infinity. Okay. Here's another example that deals with, so example 3, 257 times 0.93 to the x power. So there's no addition, subtraction, extra pieces here. It's just a semi-large initial value of 257, and then you have this 0.93 to the x power, and since the 0.93 is a growth factor between 0 and 1, that makes this a decay function. You can graph it if you like. Starts up at 257, but it does decay. There's no reflection, there's no movement, no shifting. So as the x values get infinitely large for this function, it'll decay more and more. It'll get closer and closer to the x-axis, that horizontal asymptote at 0, and this function will actually go to 0. Again, you can graph it and see that as the x values get really large, the function approaches the x-axis. You can go to the table on your calculator and see that as those x values get extremely large, again, it's just plugging into the calculator and looking at those x values. So if I started and looked at 100 or even 50, at 50 it's like 6.8. And then if I go to 100, it's already down to 0.18. And if I go down to 150, the numbers just keep getting smaller and smaller. And eventually you'll get so small that it'll start representing, like at 250, it starts, on the graphing calculator anyway, it starts representing scientific notation where that's really 0.000034, and the numbers just keep getting smaller and smaller for function values. So as x approaches infinity, for this function 257 times 0.93 to the x power, the function values approach 0, and that's what the limit of this function is, 0. All right, fourth example here. Different variable, still the same idea. So we're looking at the limit as t approaches positive infinity of 21 times 1.2 to the t power plus 5.1. So for this example, the first piece is an exponential growth formula. The number that's being raised to the exponential power is a growth factor. It's bigger than 1.2. So the 21 is just an initial value. And if you look at that growth function, if you remember the way a growth function looks, exponential, as the t values, the t value gets bigger and bigger, it just grows. It grows infinitely large. So if you look at this problem, as t goes to infinity, you end up with, 1.2 to the t power plus 5.1. For this one, it's growing, and then the 5.1 is just sort of like a little extra. So for this one, as t approaches infinity, the function itself, the behavior goes to infinity. I want to make a little note here that had that limit been same function, 1.2 plus 5.1, had that limit been as t approached negative infinity, this would have been a different kind of answer. And I just want to address that really quickly about what the answer would have been. So for this one, as t approaches negative infinity, again, you can look at the same graph if you like. It still does this growth factor. But if we look as t approaches negative infinity, that's looking from as those t values go more and more left. So if you look at this growth factor or the exponential function portion, if you take 21 times 1.2 to a more and more negative power, then what happens is that portion of it actually ends up going to 0 because you're raising a number to a negative power, which is going to make it 1 over, right? 1.2 to a negative power would be 1 over 1.2 to a positive power. The denominator will grow very large, but the fraction as a whole will grow very small and will end up approaching 0. So that portion, the 21 times 1.2 to the t power, that portion goes to 0. And if you look at the graph of this, as the t values get closer and closer to negative infinity, the function values will actually approach this 5.1 number because the graph itself was shifted up 5.1 units. And if you look at a table, and like I said, you have to sort of go put it into y1, the function itself. You have to go up into the negatives. So, if you start at 0, the function is 26.1. But if you go like negative 10, it jumps to 8.5. and negative 20, it jumps to 5.6. And if you keep going more and more negative, say negative 100, then it's like 5.10000025. So and you can keep going even further than that if you want to go more and more negative. But the idea here is those y values start to approach the number 5.1 because it's sort of sitting on this horizontal asymptote. So the portion with the exponential piece is going to 0, but you're left with this 5.1, and that's what the function value approaches as the t value gets infinitely large. So the limit here is 5.1. Okay, so here are a few examples that use the e, which again is just still an exponential function, but now it's with this natural base of e. It's going to grow continuously. So it still mimics the same behavior as a growth and decay function, right? So you have y equals an initial value times e to the kt power. And if k is positive, it's growth. And if k is negative, it just means it's decay. It's just growing or decaying continuously instead of the normal exponential growth or decay. So for this first problem with the e on it, I think we're now on, I guess it would be the sixth example. If we take the limit as x approaches infinity of e to the negative 3x, the fact that the base here is e to the negative 3 makes this a decay function. And if we take a decay function as x approaches infinity, again, you're always welcome to think of these graphically, just making sure that you put the 3 and the x and the exponent together. So in y1 it would be, actually let me move this, in your y1 it would be e to the power in parentheses of negative 3x, so you make sure you keep that together. So if you graph this, it would just sort of have a decay feature to it. And as x approaches infinity, again, you're just looking at what happens to the function as the x value gets larger and larger, and you'll see from this graph, it decays away to 0. So the limit as x approaches infinity for e to the negative 3x, because it's a decay function, is actually going to be 0 for this problem. Okay. So the next one, we're looking at the function 5 times e to the 0.07t. It's an exponential function that's growing continuously at a 7% growth rate, initial value of 5. So, you have the picture, again, graphing it just sort of helps you see its behavior. It's not necessary, but you can graph it and see its behavior. This one, grows like this. 7% growth is not a lot, so it doesn't have that sharp curve up so quickly, but it still has the growth. And it's still a growth function, initial value of 5. But we're looking as the t value approaches negative infinity. So we're trying to figure out, okay, this is our t-axis instead of x, and we're trying to figure out what happens to the function as the exponent gets infinitely small, in the negative sense, not small like it's going to 0, but if that t value goes to negative infinity, then those become negative, very negative large numbers. And what happens to the exponent is it makes it a smaller and smaller number, and so you have 5 times a smaller and smaller number that's trying to go to 0, because now the exponent's negative, and anytime you take e to a negative exponent, it would be like 1 over e to a positive, and if that exponent gets infinitely large, then the fraction itself ends up going to 0, because you divide by 1 divided by a smaller and smaller number, or in this case 5 divided by a smaller and smaller number. So or a bigger and bigger number, excuse me. So then you have the fraction itself. If the denominator gets infinitely large, the fraction itself goes to 0 every time, and the limit for this function as t goes to negative infinity is going to be 0, because it's just what happens when the input values go to the left. It just approaches the x-axis, goes to 0, and there you have it. Okay. This next one looks at the function 5.3 times e to the negative 0.12 to the t power. This is a continuous decay example. It's decaying at a continuous rate of 12%, initial value of 5.3. Again, for what it's worth, if you'd like to graph it, just make sure that you get all of the right components in with the right notation, and you put 5.3 e to the negative 0.12 x power, because you have to use x for input on the calculator. And then if you graph it, it is a decay function that doesn't have any plus or minus to shift it or negative on the initial value to reflect it. So it's just your basic continuous decay with a 5.3 y-intercept. And if you look as that t value approaches infinity, again, you're just looking at what happens to the function when those x values get infinitely large. And because this is a decay function, that exponent is going to get infinitely large times this negative number. You're still going to have e to a negative number. And the larger that negative number gets, the smaller the value gets, and the graph approaches zero. Again, the table can come in handy if you go to look at your table values. If you started at 0, the function value is 5.3, but then you'll quickly see, if you jump to 50, it's 0.013. If you jump to 100, you start getting into scientific notation, that's 0.000033, and the numbers just keep, the function values, the output just keep getting smaller and smaller. So as the t value, or the input x variable, goes to infinity, the function values get smaller and smaller, and they approach 0, and that is the limit answer for this function. As t approaches infinity of 5.3 e to the negative 0.12 t power, the function goes to 0. Okay. Here's a couple more. You have the limit as t approaches infinity of 2 minus 3 e to the negative 0.2 t power. So we're looking for t to go to infinity. The right portion, the term here, the negative 3 e to the negative 0.2, that's a decay function. Okay? And even though it's being subtracted, the fact that it's being subtracted sort of does this reflection. And if you graph negative 0.2, let's see, it's a 20% continuous decay because the negative 0.2, that's what that indicates. And if we graph this one based on the way it's run, let's see, it kind of does this number. So the negative 3, even though it's a decay function, the negative reflected it and makes it look like a growth. And if we look as t approaches infinity, for this one, the decay portion, let's see, yeah, the decay portion, if you plug in infinity for that negative 0.2 to the t, then this decay portion actually goes to 0, because you're just having a 3 times an e with a negatively large exponent, and that's going to be 1 over e to an infinitely large positive exponent. And as the denominator gets infinitely large, the fraction as a whole becomes 0. That's just the behavior of the way a fraction works. Or in this case, I guess there would be a 3 up there. But still, the denominator gets huge, so the fraction itself goes to 0. So that portion of it goes to 0, and you're left with this 2 number. And you'll see also, if you look in the table for this function, again, you can start it at the table at 0, and you'll see at 0, the function value is negative 1. But the moment you start going bigger, like if you look at 50, because again, as t approaches infinity, if you look at an input number of 50, the function value is like 1.99, a whole bunch of 9s. And if you go to 100, the calculator may show the number 2, but it's restricted to pixels and input and computational mannerisms, and it'll show a number 2, but if you arrow over to it, it's like 1.999. It's a whole bunch of 9s, and then like a 382. Even though visibly it'll show a 2 there, and it's the same thing. As the x gets larger, that number just approaches 2. So the function here, the limit as t approaches infinity for this function, the decay portion goes to 0, and you're left with that constant of 2, and that's what the limit value is. It's a 2. For the next one, just a little different, but not a whole lot, because it has this plus 4 in the exponent. So if we look, it's a decay function, right? The e has a negative power on it, but we're looking this time as t goes to negative infinity. So if we take negative infinitely large numbers and plug it in there, e will become a positive power. So we'll have 2e to a positive power plus 4, so it's just going to keep it positive. And so this ends up becoming, again, because we're going to t to the negative infinity, it sort of looks at the end that grows to the negative. I'm just going to graph it so I can sketch you a graph here. If you graph this, it ends up doing, maybe I have to zoom out to see it. Maybe I didn't input it right. 2e negative 0.1x. Nope. It does do a decay. Here we go. Let's see. It starts up, oh, way up there at 109. Okay. So it's a decay function that does this. But we're trying to look at what happens as the t values approach negative infinity. So that's this left portion of the graph. As those t values get further and further negative, the graph sort of shoots up to positive infinity, which you would expect that if you plugged in negative values for t, you'd have negative 0.1 times a negative number turning it positive. Even if you add 4, it still is a positive number. And so as those numbers get more and more negative, the exponent on e gets more and more positive, and it just stays positive, and it ends up blowing up, and the limit value here goes to positive infinity. Again, we're looking as t goes to negative infinity, and when that happens for this decay function, the function values shoot up to positive infinity. Okay, just a few more. Here we have one where we're looking at the limit as x goes to infinity of 15 minus 5e to the 3x. So we have this 5, this 15 out front is going to make it a little shifted. And the fact that we're subtracting 5e to the 3x is going to take what would potentially be a growth function, and it's going to reflect it and make it look like a decay function. But here, the e to the 3x is a growth function. It's a continuous growth of a whole lot, 300% actually, because there's no decimal on it. But the fact that it's being subtracted, again, if you graph it, it ends up doing sort of this number. Let's see. And then let's see, where does it go? It just shoots down really fast, extremely fast. And it doesn't really go in a vertical line because then it wouldn't be a function, but it does shoot down to negative infinity quite quickly because of that power of 3x that's on that base of e. But if you look at it as a growth function, the 15 or the 5e to the 3x, you just have the number 15 and you have 5e, and as x goes to infinity, x gets plugged in here, you have e to an infinitely large number, which is going to make that number, that e, grow massive, and then you're just going to multiply it by 5. So you have 15 minus an infinitely large number. And if you have 15 minus an infinitely large number, that number is just going to get more and more negative. And what happens is this function, again, this is looking as x approaches infinity, not negative infinity. That would be a different limit. But as the x value approaches infinity, again, we're looking at what happens to the function value. This one ends up, because you're doing 15 minus an infinitely large number, the answer is just going to get infinitely large in the end, and your function, the limit value, goes to negative infinity. Okay. Next example here looks at a limit as x goes to negative infinity of 5 times e to the negative 7x plus 1.5. So if we look here, the 5e to the negative 7x is a continuous decay problem, but we're going to look as x goes to negative infinity. So imagine negatively infinite values being plugged in, and we're going to have 5e, and we have a negative 7 times a negative number, and that negative number is going to get infinitely large, again, in the negative sense. But what happens is you have a negative times a negative, so you'll really have 5e to a positive power, and it's 7 times an infinitely large number, so that number will get infinitely positive as an integer, or as a real number that's going to stay positive, and then you're just going to add this random 1.5 to it. So what happens as x goes to negative infinity, is this function actually blows up huge, and it should end up going to positive infinity. And we can graph it just for visualization. And what happens for the graph of this function is, if I can find it in my graph in my window, let's see. And the table also helps too. But this one crosses at 6.5 here. But then the numbers, I mean, I'm talking they just get huge. So your graph sort of looks like this. As the x values get to positive infinity, this graph tries to approach a horizontal asymptote at 1.5. And you can see that on the graph because the decay portion goes to 0, but we're trying to look as x goes to negative infinity. So we want the left half of the graph. And you can see from the graph, as well as the table if you choose to look at the function values, when the x values get infinitely large, this left portion, the graph shoots up to positive infinity. And again, you have 5e to a really large positive number, and that number is just going to stay infinitely large the more and more negative the number gets. So the limit for this function is positive infinity. All right. So for this last one, I forgot to write, we need to go, as x approaches positive infinity, of 7.2 minus 2e to the 3x power. So again, we can think about this algebraically, we can look at it graphically, it all gets us to the same result. If we look as x goes to infinity, x is a power on an exponential growth portion of a function, even though it's being subtracted. So if we plug infinitely large values, we'll have a subtraction of 2 times e to something that gets infinitely large, because it's 3 times an infinitely large number. So that just gets even more large. And then we'll multiply it by, raise e to that infinitely large power, multiply it by 2. So what you have is the number 7.2 minus an infinitely large number. And, using some arithmetic, if you take 7.2 and subtract 1 million, or 7.2 and subtract 5 billion, you end up with a negative number that ends up getting infinitely large as well. And so the function values should approach negative infinity as the x goes to positive infinity. Again, graphically, if we looked at graphing this function, it starts, if you go to negative infinity, it's up here at the 7.2, but we're looking as x goes to positive infinity, and that just shoots down the y-axis. So if we pay attention to what the function does, as the x values go to positive infinity, the function itself shoots down to negative infinity world, and that's what we have for our limit, is the limit for this function as the x's get infinitely large, the function values get infinitely large on a negative sense. And again, the graph can show you that, using the function input from the algebra can show you that. If you just think about what happens to the numerical behavior of the function, where the exponent lives, what happens if it gets added, if it gets subtracted, and then you can sort of pick out what will happen to the number. And again, the graph helps, the table helps. You can see pretty quickly on this one that the numbers, they just get huge. Like the exponent, the scientific notation is like times 10 to the 13th times 10 to the 29th. So the number gets really infinitely large really quickly on this one. So the limit for this one goes to negative infinity. So hopefully you can understand how to plug in those infinitely large or infinitely small numbers, see what it does to the function, see what it does to the graph, be able to go and look at your table in your calculator and use some sort of representation to wrap your brain around what the function does. And the function may go to a number, especially if there's an asymptote involved, and the function may go to either positive or negative infinity. You just sort of have to watch and see which direction of the graph you're looking at in order to determine the limit.